We're now going to learn the basic a priori algorithm. Later we'll see some improvements to this basic idea, but the fundamental insight is monotonicity, the idea that an item set cannot be frequent unless all its subsets are frequent. The a priori algorithm uses one pass for finding the frequent items, then another pass through the data for finding frequent pairs, and if we want frequent triples, we need another pass, and so on. Each pass after the first can be thought of as having identified a small number of sets of the relevant size that might be frequent and therefore require a count. But the power of a priori comes from the fact that for many data sets we can eliminate almost all sets from candidacy and thus greatly reduce the number of counts we need to maintain in main memory. We can think of the a priori algorithm as a two-pass algorithm, since that is what it needs to find frequent pairs. But as we just said, if you want to go past pairs to larger item sets, then you need k passes to find frequent item sets of size up to k. The monotonicity property, which a priori exploits, says that if a set of items appears in at least S baskets, then so does each of its subsets. That should be obvious, since there are S baskets that contain all members of the set, and so surely these S baskets also contain any of its subsets. And there may be more baskets that contain the subset but not the full set. Now we actually use this definition in its contrapositive form. For example, when we're looking for frequent pairs, the key observation is that if an item I does not appear S times by itself, then no set containing I could be frequent. Because if, say, the set of I and j appears in S baskets, then surely I appears in all those baskets and maybe others. This is all really obvious, but it's also essential, and I want to make sure everyone is on board. On the first pass, we count the number of times each item occurs. We want to do this in main memory, and unless the number of items is beyond billions, we can set up an integer count for each item in main memory. After the first pass, we see which items appear at least S times. These are the frequent items. Incidentally, if all we want is to tell whether or not an item appears S or more times, then it is sufficient to count up to S and not add ones beyond that. So if, say, S is 10,000, then we only need to keep 2 bytes per count regardless of how many times items might appear in the data. Now let's look at pass 2, where we read all the baskets from disk again. And as in the naive algorithm, we're going to try to count pairs in main memory. But now we use monotonicity, so we only have to count those pairs of items, both of which are among the frequent items. So for example, if only half the items are frequent, we need to count only a quarter of all pairs. Okay, the main memory we need depends on the square of the number of frequent items only, but there's a small amount of additional main memory we need for a table that lets us know which of the items are in fact frequent. As we read a basket from disk, we look at all its items and ignore any that are not in the table of frequent items. From what remains, we generate all pairs and increment each of their counts. So here's a picture, the first of a series we're going to use to compare different algorithms. The rectangles each represent main memory and how it is used on each pass. On the left, we see the first pass of the a priori algorithm. We need space in main memory only for the counts of the items, and we show it as occupying only a small fraction of main memory, because typically we will need much more main memory for the second pass. In the second pass, we distill the item counts from the first pass down to a list of frequent items. This list is probably implemented as a hash table or similar structure, so given an item, we can quickly tell whether it is frequent. The rest of main memory is available for counting all the pairs of frequent items. For a priori to work in a reasonable amount of time, these counts must all be able to fit in main memory. If there's still too many counts to maintain in main memory, we need to try something else, a different algorithm, splitting the task among processors, or even buying more memory. We might suppose that when you're counting only pairs of frequent items, you have to use the tabular method to store counts, since we hope that only a small fraction of the possible pairs need to be counted. Since the numbers associated with the frequent items are not likely to be consecutive, it looks like we can't use the triangular matrix with counts for only the pairs of frequent items. Or if we did, we'd use just as much space as if we were counting all pairs, and we might not have that much space. Fortunately, there's a simple trick we can use. We renumber the frequent items starting at 1, and on the second pass we store a table that translates the original integers used for all items into the new numbers for the frequent items only. This table also tells you whether an item is frequent or not, since it will not appear in the table if it is not frequent. So here's the picture of a priori again. We show the table on the second pass is taking more space than before, since it stores 2 numbers per frequent item and needs to store each item, even those that are not frequent. So we can index into the table given an old number and find either its number among the frequent items, like 1, which has new frequent number 1, 3 has new number 2, or, as in this case, we can find it's not frequent. There are better ways to organize the table that saves space if the fraction of items that are frequent is small. For example, we could use a hash table in which we stored only the frequent items, with the key being the old number and the associated value being the new number. What we're not showing is a table that all algorithms may need, one that translates from the representation of items in the raw data to the old numbers, that is the consecutive integers that we used for all the items. The idea used on the second pass extends to later passes that construct larger sets. Let's use the term k-set for an item set with k members. Then there are 2 collections of k-sets associated with our effort to find all the frequent k-sets. C sub k is the candidate k-sets. These are the sets that, based on what information we have from previous passes, might be frequent. At least we can't rule out the possibility of their being frequent by using monotonicity, so we have to count them. And then the result of the kth pass we'll call L sub k. This is the subset of C sub k, consisting of those k-sets that are found on the kth pass to be really frequent. Now here's a picture of the full a priori algorithm, including not only pairs, but a suggestion of the process for larger item sets. In fact, this is the picture for a whole family of related algorithms, where each algorithm is characterized by a different way to construct the set of candidate pairs C2. Each pass consists of a filter step where we look at the candidate sets for the pass and select only the frequent sets. That is, CK is turned into LK. Each pass also has a construction step where the candidates for the next pass are constructed from the frequent sets for the current pass. That is, on the kth pass, CK is constructed from L sub k minus 1. We start with C1, the set of candidate singleton item sets. These are all items, since we have no way of eliminating any items without looking at the data. The filter step for the first pass counts the items and finds those that are frequent. So the set L1 is just the frequent items. From L1, we construct C2, the set of candidate pairs for the second pass. In this case, we don't actually do anything. The set C2 is defined implicitly from the list of items in the set L1. Okay. The filter step for the second pass counts all the pairs in C2, and the result is the truly frequent pairs of items. We can proceed like this from the frequent pairs. We construct C3, the candidate triples, by a technique we'll describe on the next slide. Then we filter C3 to get L3. From that we construct C4, and so on. We can describe the a priori algorithm for item sets of all sizes as an induction on K, the size of the item sets we construct. There is one pass for each K. The basis is that C1 is the set of all items. Strictly speaking, C1 consists of all the singleton sets, each of those sets containing one of the items. Given the set CK, we construct LK by making a pass through the data and counting each set in CK. Those sets whose counts get up to the threshold S become members of LK. The other part of the induction is how we construct CK plus 1 from LK. We look for sets of size k plus 1, each of whose subsets of size k, those you get by dropping one element, are in LK. You have to be a little careful how you organize the search. For example, you wouldn't want to enumerate all sets of size 4, and for each one test if each of its 4 subsets of size 3 are in L3. A better idea is to start with some set in LK. For example, assume k equals 3. We might find the set, let's say 135 is in LK. Now look at each item whose number is higher than any in the set, say 6. Okay. This set might be in C4. We already know its subset, that is the subset of, well, we're talking about really 1, 3, 5, 6. Now we already know that its subset 1, 3, 5 is in L3. So we have to test 3 other sets. We have to test, 3, 5, 6, and 1, 5, 6, and I guess 1, 3, 6. And if all 3 of these are in L3, then we would put this guy, 1, 3, 5, 6, in C4. Then we're not done with starting again with 1, 3, 5. We might then throw in the element 7 and so on, then 8 and 9, all the time searching for sets of size 4, each of whose subsets of size 3 are known to be frequent. The space needed on the kth pass is proportional to the number of sets in CK. In principle, there could be as many as n choose k candidate sets of size k, if there are n items. So the space requirement could grow painfully each time k increased. But in cases where this method is used in practice, the support threshold is high enough that as k increases beyond 2, the number of candidate sets that can be formed from the frequent sets on the previous pass actually decreases, doesn't increase. Thus, the memory requirements peak at k equals 2, and that's why we concentrate on finding frequent pairs, and why the more advanced algorithms we'll see in the next unit differ from a priori in how they handle the pairs.